So today is day 2 for chapter 3. We already did scatterplots. Now we're going to look at this famous term called correlation. And hopefully by the end of what I'm going to teach you, you're going to quit using it the wrong way, which is not your fault. It's just one of those things. This is not used properly in most cases. So let's see what this is all about. Correlation is a numerical summary. So you can't say that, the amount of calories a person eats and their height are correlated. No, they're associated, all right? Variables are associated. Correlation coefficient is a number summary like mean, median, mode, IQR, standard deviation, all of those things are a descriptor. So it measures the strength and direction of a linear relationship between two variables x and y. All right, the notation for it is this lowercase r. And you notice it's the strength and direction of a linear relationship. So if you find something that is strong, that shows a strong relationship in an r value, it doesn't tell you that it's linear. It just tells you that, I've got a strong relationship. I need to look at my scatter plot to see if it's actually linear. So just because you get an R value that is really showing strength does not mean that you have something linear. So here's your formula. Okay, let's break this down. While I'm thinking about it, I think there's a homework problem where they say, calculate R from scratch using this formula. Nah. Just calculate it on your calculator. Let's not get carried away here. All right, x sub I are just the x values that you would see in an ordered pair. And from that, you're subtracting the mean and dividing by the standard deviation for your x's. And then you have all of your individual y's taken from ordered pairs minus the mean of the y's divided by the standard deviation of the y's. Do these two things look familiar? Do they happen to ring a bell perchance? Like maybe they're standardized, like they're z values, like this is a z value and this is a z value. And so it really doesn't matter if you're measuring like calories for x and then height in, let's say, meters for y. You lose all the units. So you take them and individually, like for each x sub I and each y sub I within an ordered pair, you get that standard value for both and multiply them together. So let's say you have 20 ordered pairs, so you're going to get 20 products. Then they get added up. Remember, sigma means add them up. And from there, you're averaging them. But you're doing it the way we did it with standard deviation with n1 over n minus 1 instead of n, 1 over n rather. And that's because we're dealing with degrees of freedom again, that famous thing. So this is the formula for calculating correlation. It's the average of the products of the standardized x's and the standardized y's. That's all it is. And you might not see that with all of this sort of weird math notation, but that's what it amounts to. So, fun facts. You lose your units. I think I just got done saying that. So it allows us to calculate R while combining unrelated variables. Okay, another thing to note that let's just say I want to, measure food intake with calories, but I don't want to measure the height in meters. I want to do it in inches or feet or anything like that. All right, you're going to get the same z-scores whether you're in inches, feet, meters, centimeters, because all the scaling changes within the formula for standardizing, and you end up with the same z-scores. It doesn't matter which variable you call x or y. So the explanatory and response kind of setup is important for just about everything in this unit except correlation. If you reverse x and y, and you call y the explanatory and x the response variable, you're going to get the same R value. Okay, both variables must be quantitative, so no categorical like eye color or gender or race or anything like that. That doesn't come into play because those things can't be quantified. So how to interpret this? So a positive R value indicates a positive association between the variables. And you notice I didn't say a positive R value indicates a positive correlation between variables because that's a misuse of the term. A negative R indicates a negative association. So now correlation falls between -1 and 1. So 1 is the strongest possible positive linear relationship you can have as far as an R value goes. And -1 is the same for a negative slope, let's call it, a negative relationship. All right, so if you get a 1 or a -1, which you probably won't in your whole life, but if you get close to it, then you're going to see perfectly lined up data points along a straight line, or very close to it, either in the positive or the negative direction. Okay, correlation values near 0 indicate a very weak linear relationship. Okay, again, I think this is going back to what I said earlier about doesn't matter if you measure something in a different metric, you're going to get the same standardized value and the same R value if you change units. So correlation only measures the strength of a linear association between two quantitative variables. It can't be used with curved relationships. This is why it's so important to look at a scatter plot first and decide if you have something linear from that, as opposed to hoping that your R value will show something that's linear. It actually doesn't, right? It can show a linear strength and it can show direction, but it doesn't actually show linear. I mean, just because it's showing linear strength, you have to verify the linear first, okay? So that's important. Where did my pictures go? There they are. All right, so don't use R with something curved, because you can put data that fits something exponential in your calculator and it'll generate an R value for you because it doesn't know any better. You have to know better. So to use correlation, these conditions must be met. Okay, your variables have to be quantitative. You must have a linear relationship as verified in a scatter plot. And you need to check for outliers. And I think you're going to see in a little bit that when you have outliers present, it has a big impact on R, on your correlation. So correlation is non-resistant to weird and unusual values. Oh, there it is. Just like the mean and standard deviation, correlation is strongly affected by outliers. It's non-resistant. So you can actually decide, all right, this point and this point are outliers. I'm going to figure out R with them in my linear system. I'm going to then take them out and recalculate it. And you should see something that would verify an improvement in linear strength when you take those outliers out. And just remember, R is not a complete description of a two-variable data set. All right? The scatter plot is a great descriptor. R is a helpful descriptor too. The least squares regression equation that we're going to get in a day or two is going to be extremely important. So this is a tool in your toolkit, but use it properly. Okay, so what can you expect from a scatter plot? See how this is pretty much almost a circle? I mean, it's got a little bit of a line up to it, but it's pretty much a circle. Okay, correlation equals 0. Okay? Now it's getting a little better organized. Not much, not much. This is a pretty low R value, and I'm not meaning low by the negative. I mean as far as it lining up well to a straight line. Okay, it's getting a little better here. And you notice that they're changing from 0 to negative to positive to negative to positive. But it doesn't matter. You could take the mirror image of this and it would still just be an R of what, negative 0.5? Here is negative 0.7 lining up better. Here's 0.9. And you might think that it should line up better than this. But that's It's a pretty good linear model, but it's not like riding along a single line. And here's a correlation of negative 0.99. Again, there's still a little bit of scatter, but it's lining up pretty well. So let's get a little bit of a grip on this. Let's see. Correlation does not exist on a linear scale. Okay, it fits a linear model, but the scale of the number itself does not behave like a line. So thus, a correlation of 0.8 is not twice the linear strength of a correlation of 0.4. It's actually a lot more. Okay, does that make sense, the first bulleted point, now that you've seen the second one? Now, we will come up with a measure that's similar to correlation where you can do proportional reasoning, but not with R. No proportional reasoning with this numerical summary. But you can say this is a lot stronger linear relationship at 0.8 than it is at 0.4, but it kind of begs the question, what starts something that's a strong linear relationship? So a moderately strong to strong correlation begins at an R of 0.8. You would think it would be less than that. But once we look a little further in a few days, you'll understand why this is only moderately strong to strong, okay? And in fact, this may be weaker than you might think. So what can go wrong? Again, correlation does not equal causation. Be really careful with this. You can get things that are just comically unrelated that are almost perfectly lined up and will give you an extremely high R value, right? We're going to cover that again in a few days. Just absurd things. Right. Scatter plots and correlation coefficients never prove causation. In fact, we never prove anything. Never prove anything. We would need an experiment to really show any kind of causation, and this is not it. So sometimes you can have a really strong relationship between two variables, but there may be something hidden underneath, a hidden variable that stands behind a relationship and is actually determining it by simultaneously affecting the other two variables. That is a lurking variable. We're going to do a day with how associations happen, and you'll see this idea of a lurking variable a little better. So, a scatter plot of damage in dollars caused to a house by fire shows a strong correlation with the number of firefighters at the scene. So, I guess the more firefighters are at the scene, the more money in damage is accrued. But damage doesn't cause firefighters, and firefighters do seem to cause some damage, spraying water and chopping holes. But compared to the fire, maybe not so much. So does that mean we just should not call the fire department? You know, we get more people there, that's it, my house is gone. Well, there's an underlying variable that leads to both more damage and more firefighters, and that's the size of the fire. And so if you're just looking at the two as, quantitative variables and them being very strongly linearly related, to say that one causes the other is just absurd. There's just a third variable that's driving both that we're not even thinking about. So don't say correlation when you mean association. Correlation is a number summary. It's not a relationship. It's not an association. Those words are used just as descriptors. Correlation is a number summary. So the word correlation should be reserved for measuring the strength and direction of the linear relationship between two quantitative variables with the value R. Watch out for this. This may come again a little later, but extrapolation. I don't know if you've learned this in earlier math classes, but that's where you make predictions outside the values of X for our model. And they are unreliable, unsafe, and should not be trusted. Okay, so if this year I have so many locusts and they're starting to eat crops, and the next year I have more, and the next year I have more, and the next year I have more, and the next year I have more. Is that going to go on forever? Or will that population ultimately reach its zenith and then start crashing and dying off? For various reasons, no food, disease, whatever. All right, so if you're going to make predictions based on any kind of model that you develop with a set of X values and you start predicting beyond that set of X values, you're asking for trouble. Now, if you want to make predictions within that domain of X values, then you're probably in pretty good shape. All right, so this is something that I'm just already set up in my calculator for, but you can pause. Now, the correct calories are actually explanatory, and the guessed calories are response. This is a little backwards to what you would expect in a table. Typically, the explanatory comes first left to right. It comes first in the top of a table, top row, and the response variable here would come second or bottom of a horizontal table. But somehow or other, I guess they're just making you, be flexible. So pause this, enter the numbers, put this in your first list, correct calories, and to the right of that, put your guessed. Okay, so I have got these in, and we'll start out with the end spire, and here they are. So let's kind of run through the process. Let's start with a scatter plot. All right, so we're going to go home, and we're going to scoot over, down rather, and then over to a stats graph. So here it is. We want the correct calories to predict the guessed. And, looking at this, it does seem to line up this way. And it's not super strong. Now, you might look at these two and say, whoa, these guys may be outliers, because if you picture a line through here, these would be offset. So what's going to happen here is that these 2 points will actually take a line that would normally go through and maybe pull it up a little bit, and that's a distortion, right? So it's going to change your correlation to have them there. It would change any kind of a linear model that we would build, which will come later. But I'm just going to leave them in here, and I'm just going to say that this is a moderate linear, positive linear relationship between correct calories and guessed calories. And I believe that you can add a, let's see, maybe you can add a regression line to it. Not going to let us. If we had already done the regression equation, then we could add it. So I guess we'll just leave it alone. So let's go back into your home screen and open up a calculator page, because we want that R value. So let's go to Menu and Statistics and Stat Calculations, and we want a linear regression. Now, it's not mx plus b. That's algebra 1. Right? We want a linear regression a plus bx. So this would be your y-intercept, a, and b would be your slope. So let's pick that. And my x list was the correct calories, and they're used to predict the guessed calories. So let's just go ahead and tab down and leave everything else there. We may need this F1, just remember it. We won't need it today, but this is a good thing to remember. Okay, so there's your correlation. Pretty high. Okay, we can say it's maybe moderately strong. So I'm actually contradicting myself a little bit. Now we need the R squared for another day. This was your slope, and this was your y-intercept. It tells you up here. Okay, so there's your R value. So let's go to the other calculator, and I'm just going to maybe minimize this to get the busy off my screen. See if I can't move that over. And I have the data put in here, so I'm going to quit out of here, and then I'll do Stat calc, and I want lin reg a. I don't want the ax plus b. I want the a plus bx. All right, x list is L1, y list is L2, and I will show you that you probably could use this, but we'll save this for later. And calculate, and whoops, I forgot a step. Okay, this is really important, and I'm kind of glad I forgot it. We need to turn the diagnostics on. This is a weird feature of your TI-84 style calculators. So do second and 0 for catalog. And let's find the letter D if we can find it here. Here it is. It's right next to this X inverse key. And you can just scroll and find it yourself without doing that, but this will get you here quicker. Diagnostics on. And just hit enter. All right. So I'm just going to go ahead and do second enter until I get that linear regression back. And now there it is. All right, so there is all the same stuff that we saw before. So 0.8245 is your correlation coefficient. See that? So that's your calculator moves. And I think there's just, after this is your homework page. So there it is. It's not super extensive, but knock that out, and then we will move forward. So on that note, I'm going to bid you a fond farewell.